Welcome everyone to today's long-range colloquium. For those of you who haven't seen me, my name is Evert. I am an assistant professor at the Niels Bohr Institute in Copenhagen. And this colloquium today is part of a long-running series in the meantime by the Virtual Science Forum. And I will put a link in the chat in a moment. And we are a group of colleagues all over the world organizing different virtual science events. This one, but I highly encourage you also to check out the website and look at the Speakers Corner or the various workshops that are going on. And of course, if you're interested in joining us, that would be very nice. We're always looking for extra people with new ideas and suggestions. You'll find more info about that also on the website. And this is a good point also to acknowledge the support that we're getting from the Kavli Institute at TU Delft in the Netherlands. I should say up front that our speaker is very happy to answer questions during the talk. So please feel free to unmute yourself and ask a question. You can also use the raise your hand feature and I'll unmute you or you unmute yourself at a good point in time. And the other option, of course, is to write in the chat if you'd rather not speak. And if that's the case, then I'll find a good moment to interrupt our speaker and ask the question on your behalf. Please note that the talk is being recorded. Should say that for the record. And our event today, the Long Range Colloquium, already has a very impressive list of speakers. And I am very thrilled to be able to add Xia Chen today to that list. Xia is a professor at Caltech, and she has a very broad interest in all things condensed matter systems. She is well known, of course, also for her work in topological systems from her time already before when she was a student with Xiaogang Wen and Isaac Chuang at MIT. She's also worked on tensor network systems, dynamics of many body systems, many more interesting works. And has been awarded a bunch of prizes also for those works, one of which is the very prestigious New Horizons in Physics Award last year, from which I personally benefited also a little because at that time I was still at Caltech and the reception and the celebration for that were very, very wonderful, I should say. And recently, Xia has taken an interest in Fracton systems, and that's also what she's going to be talking to us about today. So I would like to hand over the floor now to you, Xia, and we're all looking forward very much to your talk. Please go ahead.
Thank you, Ever. That's a very nice introduction. So I'll take over and I'll try to share my screen. Host disable participant screen sharing.
That will be fixed.
I think you need to allow me to share my screen.
There we go. Okay. You should be able now. Thanks.
Yeah. Right. Good. Good. Okay. All right. Yeah. So it's great to see everyone, old friends and new friends. And today I'm going to be talking about Fracton. And so Fracton has been my obsession for the past couple years. And this is a relatively new topic, but of course it's connected to things I've been working on, mostly the topological system. So the work I'm going to be telling you about is about thinking about Fracton using a different theoretical framework, the Chern-Simons theory. And so this is, of course, a tool that's being heavily studied and heavily developed in condensed matter and field theory. And it has been applied to a range of topics, but I want to tell you today how we try to use it for the purpose of study of Fracton. Okay, and as Ever has mentioned, please interrupt anytime if you have questions. I welcome that because I want to make sure that everything I say is clear and not confusing. So yeah, thank you. So this work is done in collaboration with these wonderful people that I put on my slide. Xiuqi is a student in my group, and as well as Wilbur. And Meng Cheng is a professor at Yale, and Michael Levin is at Chicago, and John McGreevy at San Diego. So I could only have done this with the help of all these wonderful people. And the paper is on arXiv, and so it's still on arXiv. Okay, good. Let me get started. So Fractal is as I said, a relatively new topic, and especially the word Fractal is made up. It's something that we just came up with in the process of working on a bunch of models. So basically the field kind of started or restarted a couple years ago, around 2015 and 2016, when a group of condensed matter people got interested in a bunch of three-dimensional, very exotic models. So the name, as I said, is made up, and it's not probably not the best word, but what it's referring to is some common exotic feature about point excitations in these three-dimensional systems, and in particular, a common theme among these models is that they host point excitation, gap point excitation that can't quite move. Somehow, once they're created, they get stuck. Okay, and so I want to introduce this topic just by giving you a sense of what can happen in very specific models. For example, one of the prototypical model that people talk about and study a lot is so-called the X-cube model. So X-cube model is a very strongly interacting spin model on cubic lattice, and you can see that the pictures I draw are the interactions in the lattice. So it's cubic lattice with spins with qubits on the edges, and then X and Z are referring to the poly X, poly Z, sigma X, sigma Z operator for the spins. And the Hamiltonian term is like this. There's a bunch of terms associated with each cube, and they are a tensor product of sigma X around the cube. So it will be a 12-body interaction, very complicated. And then there are these 4-body terms at each vertex that involve 4 of the sigma Z around the vertex in X, Y, Y, Z, and ZX planes. Okay, and of course the Hamiltonian would be a sum over all these kind of terms. And the model is of course very contrived. It's made to be like this, such that all the Hamiltonian terms commute, and the model is exactly solvable. That's why we're interested in that. And it turns out that this model has some very weird property. One of them being that if we put the model on a three-dimensional torus, meaning that we have periodic boundary condition in all 3 directions, and then we can calculate the ground state degeneracy, and turns out the ground state degeneracy is a huge number. If you take the log of the ground state degeneracy, you find that it scales with the linear system size. So the log is 2 times Lx plus 2 times Ly plus 2 times Lz minus 3. So it's a very big, extensive ground state degeneracy. Okay, so this is one surprising property. The other aspects that's unusual about this model has to do with point excitations. And in particular, we can imagine point excitations being made when the Hamiltonian terms gets extra energy. And because all the terms commute, so we can just assign energy to these terms. For example, the vertex terms can be excited by applying a string operator like this, like a single string of sigma X. And once we apply that, some of these vertex terms will be violated, meaning that they anti-commute with the string and gets a high energy, And in particular, for this one, we excite the purple and the red term at each of the ends, at the left end and the right end. Then similarly, we can do this in the other 2 directions as well. We can apply string operator along X and Y and Z direction. But what happens is that, as you can see, the composite of excitations as being made by the string operator going along different directions actually give you different type of excitation, and they carry different colors. And this is important because once we try to create a pair of excitation and then take it to do a turn, to turn into a different direction, it actually changes into a different species of excitation. So this is different from our usual idea of how quasi-particle excitations can be made. Usually we can pop out a pair of excitation, then we drag them around, and then they can move. But here we create a pair, and then if we try to move it in a different direction, it changes into a different type of excitation. And because of that, something has to be deposited at the corner, meaning that there's still some excitations left at the corner. And because of that, we say that these type of excitations are the so-called linear excitation. Of course, this is again a name that we made up, meaning that these excitations can only move along a line. And that is one of the hallmark of the fractal model, that point excitations somehow have restricted motion. Okay. And it can be even more extreme in the sense that let's consider the excitation of the cubes. And if you want to make excitation of the cubes, it turns out that you have to make 4 of them at the same time. You can't even just make 2. Every time you make these cube excitation, you make 4, and the way you make them is by applying these sigma z's on a bunch of edges that's sticking out of a rectangle. So you can do this. And when you do this, you see that only the 4 cubes at the corner gets a higher energy, so they become point excitations. And every time you do this, you create 4 excitations as a set. And because excitations of this type are created 4 as a set, there's basically no way to just take one of the excitation and move it, take one of the cube and move it. So these cube excitations are actually what we call fractal excitations, meaning that they don't move, they don't have motion in any direction, not like the linear. The linear one can still move in a line, and these ones, they just get stuck by themselves. Okay, and so of course, more generally, we refer to this set of models as fractal models. Another feature of this model is that if we make dipoles of these either fractal or linear excitations, meaning that we take a pair of them, and once we take a pair of them, then they start to gain more mobility. For example, if we take a fractal dipole, which is connected in the z direction, then this pair of fractal dipole can move in the xy plane. And similarly, if we take a linear dipole also connected in the z direction, then it can start to move in the xy plane. And these are what we call the planar excitations, meaning that they move in a 2-dimensional plane. Okay, so this is one of the people's favorite model for studying fractal. It's simple, it's exactly solvable, it's very explicit, and you can talk about a lot of things for these models. On the other hand, fractal has been studied from a continuous field theory perspective, and one of the most prominent one is the so-called tensor gauge theory, which the study was started by Michael Pretko in 2006. And he proposed that we can generalize the usual gauge theory that we know, just electromagnetism, and somehow get a fractal feature out of it. So the idea is very simple, so let me just quickly go through it. We take the usual gauge theory we have with a vector gauge field, with a vector electric field, for example. So this is electric field in XYZ direction. And in the usual electromagnetism, we have Gauss's law, which says the divergence of the electric field is equal to charge, right? And because of that, we know that there's a conservation law of total charge conservation, that within the whole space, the total charge has to stay 0 if it's originally 0. And because of this, when we create charges out of vacuum, we have to create a pair. We have to create an electron and a positron at the same time. But once we create them, they're free to move, right? Their motion of individual charge doesn't violate charge conservation. So where do we get the fractal feature? Well, we need to generalize this setup a little bit by taking the electric field not to be a vector, but to be a rank 2 tensor, meaning that it has two indices, two spatial indices, E, I, J, and Ij can take value in X, Y, and Z. And when we do that, we need to change Gauss's law. Now, instead of having just one derivative, we have two derivatives acting on the electric field, and then we get the charge. And correspondingly, the conservation law also changes. Instead of just having charge conservation, it turns out that with this generalized Gauss's law, we also have dipole conservation. And dipole conservation turns out to be the key for why the fractal nature can emerge, because now if we think about popping something out from the vacuum, we can't just pop a pair of electron and positron because that comes with a non-zero dipole. And the only thing, well, the minimum thing we can do is that we pop out a configuration like this, where we have 4 charges, 2 positive, 2 negative, and they are arranged in this kind of geometry with the charges at the corner. And once they are created, of course, this is allowed because total charge is 0, total dipole is 0. And once this configuration is created, we can't just take one of the charge and move it, because that will violate dipole conservation. So in this simple setup, we also see how fractons can emerge. Okay, so this is just to give you some.
Yeah,
yes.
I thought you were pausing. There's a question in the chat, namely, does this make it an SU2 gauge? That's a question.
Sorry, what?
The question is whether that makes this an SU2 gauge theory.
Does this make an SU2 gauge theory? I don't think so.
Maybe
so the gauge field, the vector potential, for example, is still U1 degrees of freedom. Everything's Abelian, and it's just the gauge fields are symmetric tensors, symmetric rank 2 tensors. Yeah, I think the version I know works for Abelian gauge fields, not non-Abelian ones. Yeah, thank you. Yes, please interrupt me. Okay, so this is just to give you a sense of what fracton is and what we are talking about when we say fracton. So, of course, there's a wide range of activity in this field. People study these models from all kinds of perspectives, dynamics, entanglement, model construction, and even realization. But what we are trying to do, and what I'm trying to tell you today, is that we try to come up with a different way of cooking some models. And this is because my previous work has been mostly focused on these lattice models of fractons, especially X cube and models related to that. And we did a lot of things with it. But you can only do so much with lattice model, and especially exactly sub model, and they become very complicated to study very quickly. So my hope is that we can come up with a different framework which capture a lot of the features that we see in the XQ model, not necessarily this tensor gauge theory, but the XQ model, and then being a more convenient and more powerful theoretical tool so that we can go further in terms of understanding the fractal physics. Because the fractal physics, from my perspective, the biggest problem is that we have a range of amazing models, but we still need to connect the dots. Like the tensor gauge theory I'm talking about and XQ model, they all show some similar feature, but they also look very different. So the hope is that by exploring more framework, more approaches, we can have a more a holistic, global view of what is this fractal order that we're talking about. Okay, So let me tell you how we try to use the Chern-Simons theory to study fractons. And there are actually already papers about Chern-Simons theory and fractal. For example, Yi, Yu, and collaborators at Princeton wrote papers about using Chern-Simons terms to study fractal in higher rank gauge theories. That's a slightly different thing than what I'm going to talk about. And the version I'm going to talk about is actually a very basic. So let me tell you where my starting point is. So this is my starting point. This is the 2+1 dimensional Chern-Simons gauge theory with U1 gauge field. Okay, so the basic version was U1 gauge field. So these AIs, they are U1 gauge fields. And the first term is the Maxwell term, is the E squared and B squared term that comes from the Maxwell. And the second term is of course, the topological Chern-Simons term. And we're all familiar with the form of the term. It's ADA. And then here I've put some index on the gauge field, meaning that I can have more than one component of the gauge field. I label them by I and J, and the coupling is given by a matrix, this Kij matrix, and in particular, from everything we know about Chern-Simons theory, this matrix has to be a symmetric integer matrix in order for everything to be well-defined and consistent, and this has been well studied in 2+1D, of course. For example, we know that if K is equal to 1, if K is just a number, then we have only one of the U1 gauge field. And K is equal to 1, then this is actually describing the integer quantum Hall effect. And if we make K a larger integer, like K equal to 3, then we have the nu equal to 1/3 fractional quantum Hall effect. And if we have more than one component of the gauge field, for example, if we have 2, then this K become a 2×2 symmetric integer matrix. For example, it can be of the form 0, 2, 2, 0. And then this is representing what's called a Z2 gauge theory or Z2 toric code, one of the simplest gauge theory that we can think about. Okay, so of course this is very well studied and very well understood, but this is 2+1D, and what we are trying to do is to take it into 3+1D. And the way we're going to take it into 3+1D is not by making the gauge field into a 3+1D gauge field. We're still taking 2+1D gauge fields. So this mu and nu and lambda, these Greek letter labels, they still take value in 0, 1, and 2. Okay, so it's still 2+1 dimensional gauge field. But the way we're trying to make it a 3+1D theory is by taking these component labels, this big I and big J, we take them to be an infinite set. Okay, so it does not just take value from 0 and 1, it actually takes value over all integers. Okay, and of course, when we do this, this matrix K become an infinite dimensional symmetric integer matrix. Okay, and why are we trying to do that? Why do we want to do that? Well, the simplest motivation is this. Okay, let's think of the simplest situation of what this K matrix can be. In the simplest case, an infinite dimensional matrix can just be simply diagonal. Okay, and everything off diagonal is 0. The blank area is just 0. So what's going on is just that every A field has a self-Chern-Simons term with a coefficient of 3, and then everything else is, the gauge field don't couple with other gauge fields. And we know what this is representing physically, right? Because if we only have one component of this, this corresponds to one copy of the nu equal 1/3 fractional quantum Hall. And if we just put them together and sum them over, this corresponds to a stack of a fractional quantum Hall, just not coupled to each other, just a pure stack of fractional quantum Hall. And this is actually a Fracton system. Okay. First of all, it's a 3+1D system. And secondly, it has many of the weird features that we see in Fracton system. For example, the ground state degeneracy of the system, if we put it on a three-dimensional torus, so periodic boundary condition in all directions, then we find that the ground state degeneracy is exponential in the height of the system because every layer contributes a ground state degeneracy of 3. So naturally, this is 3 to the nth power, and where n is the height of the system. Secondly, all the quasi-particle excitations move in planes, moving xy planes only, meaning that they are planars. So of course, they're not quite fractons. It's not like they don't move at all, but still their motion is restricted to each of the individual xy plane, and there's no way for them to hop between the planes because the planes are not coupled to each other, and all the planes are gapped, so everything's stable. So the quasi-particles, they can only move in place, and that's what we consider as Fracton feature. Okay, and moreover, if you take a cylinder in the system and calculate entanglement for the cylindrical region, we would expect an area law term, and that's expected. But then, apart from the area law term, we would find a subleading term that's linear in the height of z, and that's easy to understand because each of the plane will contribute a constant term in terms of topological entanglement entropy for that fractional quantum Hall state because it's a topological state. So every slice that cuts through the cylinder will contribute a constant. So when we take the whole cylinder, it will have a subleading term in entanglement entropy that's linear in the height of the cylinder. And this is, again, a feature that we see in the XQ model and many other of the Fractal models. Okay. So even though this is a totally trivial model, being just a stack of two-dimensional fractional quantum Hall, we should consider it as a Fracton because it shares many of the key features of a Fracton system. Okay. But of course, this is a very trivial type of Fracton. It's just a stack of gap 2D layers. We understand everything about, pretty much everything about the 2D layers. So when stacked, there's not much new about it. But of course, the question is, can we get anything more non-trivial starting from this point by making the theory slightly more complicated? And it turns out that yes, once we start to put in off-diagonal terms into the K-matrix, the theory immediately becomes very interesting and very exotic. Okay, so let's just take this example, which we call the 131 matrix, where the diagonal is still 3, and then the second diagonal, the secondary diagonal, are populated with 1s. Okay, but then everything else is still 0. Away from the secondary diagonal, excuse me, it's still 0. And then we take periodic boundary condition, so we have a 1 here and a 1 here. Okay, so it's very minimal generalization of the previous case where it's purely diagonal. And this K-matrix actually has been studied 20 years ago when people considered a so-called three-dimensional fractional quantum Hall system. And the idea is that it can describe a layer material where each layer could say originally be in the nu equal 1/5 fractional quantum Hall system, but then we considered a situation where the layers are coupled through Coulomb repulsion. And then because when the layers are coupled through Coulomb repulsion, the electron in the top layer will try to avoid the electron in the bottom layer. And you can imagine that in Laughlin wave function, this would contribute to some Zi minus Zj term in the Laughlin wave function, but involving electrons in neighboring layers, right? And that's why these off-diagonal terms can show up, that we not only have Zi minus Zj within a layer, we also have Zi minus Zj between layers, and correspondingly, we have a K matrix like this. And once we do that, things immediately become too interesting almost. For example, one of the questions studied in this paper is if we introduce a flux in one of the layers, a 2 pi flux in one of the layers, then how much fractional charge is accumulated? Okay, and in particular, because now we have a layer structure, we can ask how much fractional charge is accumulated on every layer throughout the stack. If the system is described by a Chern-Simons term like this. Well, it turns out that this is, of course, related to the question of the statistics between the quasi-particle, quasi-holes, right? Because quasi-particles and quasi-holes can be exactly generated like this. You insert a flux and then accumulate some fractional charge, and then you move them around. You see the statistics. And it turns out the statistics goes like this, that it goes as some irrational number. There's some square root of 5 involved, and it's an exponential in terms of the distance between where the quasi-particles are centered. So if you insert a 2 pi flux in this layer and a 2 pi flux in that layer, the statistics between these two will be given by this irrational number. Okay, and of course, this is only true when the system size goes to infinity. If we have a finite number of layers of such systems, everything will always be rational, but in the limit of infinite system size, we get irrational statistics. Okay. And another very weird thing, for example, is the ground state degeneracy of the system. If we have just a pure decoupled stack of nu equal 1/5, then the ground state degeneracy on a three-dimensional torus would be 5 to the height of the system, to the number of layers, right? But once they're coupled like this, the ground state degeneracy, the formula becomes terribly complicated. And if you look at it, the leading term is the first term. The second term is going to 0, and the third term is a constant, is on the order of 1. But the first term is exponentially growing, but it's exponentially growing with a base that's a rational number again. Okay, so these are just some very shocking feature of this tridiagonal K matrix.
See,
and moreover,
I have a question.
Yes.
Okay, so if you think of this in terms of the edge theory, this will be a conformal field theory with the infinite central charge, right? And infinitely many primaries. Is there a way to understand this in a more systematic way from that point of view, as in? There are examples of conformal field theories with these kind of features when the central charge is very large, right? So,
Yeah, exactly. This the edge theory is one very interesting feature of the system, and it actually was one of the focus point of these set of works back in the days. And because they were considering like real materials of which you can measure would be these chiral edge states. And what people find is that, I don't know if they consider from the point of view of conformal field theory with infinite central charge, but what people find is that you can originally start from these chiral edges and then couple them. And one important feature is that the conductance would look different. It would be like some kind of strange metallic state. Basically, the conductance in the XY direction compared to the Z direction would scale differently. So that's how people propose to detect this kind of feature in a real material. Yeah. So this is well studied and explained in this paper and some of the related papers. Right. But for our purpose, we were looking more closely at the bulk property, because for fractons, I think we're still at the very beginning. So we're just trying to understand what's happening in the bulk for the moment. For example, we were thinking about questions like, what is the set of quasi-particles and what is a fusion group of the quasi-particles? If it's a set of nu equal 1/5 fractional quantum Hall, then we know that each layer has a Z5 fusion group. Z5, yeah, Z5 or Z10, but it's some cyclic group within a plane, and then you tensor product them together. But once they're coupled, the fusion group becomes very weird. It's ZFN, where Fn is the nth Fibonacci number. And then there's another generator which has the order of 5 Fn, where Fn is again the Fibonacci number. So the whole fusion group has 2 generators, and each of them has exponential order. And put together, they generate the whole fusion group. So compared to the papers many years ago, we're looking at the same matrix, we're looking at the same Chern-Simons theory, but we're just looking at things from a different perspective, because now we're thinking of it from a fracton perspective. And we can compare what we observe with this K-matrix to what we saw before in the X-cube model. Okay, they look similar in ways, but they also look different in others. And to compare to X-cube model, because the Chern-Simons theory, we only have planars. We only have things that move in a plane. We're not really talking about fractons and linears. So let's compare it to the planar feature of X-cube. We know that in X-cube, there are also planars, things moving in the XY plane. So let's compare to that. And we mentioned before that the planars in the X-cube model comes in the form of dipoles. So if you have either a dipole of fractons, or if you have a dipole of linears, then they can move in the plane. And the string operator that generate these dipoles are like this. So if you want a linear dipole, you apply a pair of these X string operator. So each of the X string operator gives you a set of linears, and then a pair of it gives you a dipole. And on the other hand, if you want a fractal dipole, you apply a Z string operator on a dual string, and like this. So both of them can go in the XY plane. And because the string operator looks very simple, we can figure out a lot of things about the planar in this case. For example, the fusion group would be just a bunch of Z2 subgroups tensor together, right? Each of the fracton and linear dipole would be a generator of a Z2 subgroup of the fusion group. Each of them have order 2. And then they're, so altogether, they generate a fusion group that's just a tensor product of a bunch of Z2 subgroups. And the statistics, well, the statistics, what can they be? They're sigma x and sigma z. So the statistics can just be pi statistics. If you have a fractal dipole and linear dipole, and they happen to lie in neighboring planes, then they can have a pi mutual braiding statistics. And then the ground state degeneracy, which we saw from before. And here we care about how the ground state degeneracy grows with the height in the z direction. And we know that the ground state degeneracy grows as 2 to the power of 2n, or actually 4 to the power of n. So all of these are very different from what we see in the tridiagonal K-matrix, where the fusion group involves a generator of exponentially high order, and statistics are irrational, and ground state degeneracy is exponential with some irrational basis. So what does this mean? These are some mathematical observations, right? How do we make sense or not make sense of it? Well, on the X cube side, we have a good idea of why things behave as it is. Because what we observed is that X cube model has a so-called foliation structure. Again, it's a name that we borrowed from mathematics, but this is what I mean. So take the X cube model and consider the X cube model on two lattices with slightly different size. One is Lx times Ly times Lz. The other is Lx times Ly times Lz plus 1. Okay, just slightly different in the z direction. And we asked the question of how are they related to each other? These are just the same model defined on lattices of different size, but they're very different in the sense that they even have different ground state degeneracy. Usually that doesn't happen. Usually we have the same model defined on different lattice, they at least have the same degeneracy, but fractal model is different. Fractal model, if you take different system size, they have different ground state degeneracy. But what we notice is that the ground state degeneracy can be compensated if you add an extra layer of two-dimensional toric code. Of course, you can check the number. The difference is a factor of 4, and the two-dimensional toric code gives you a 4-fold degeneracy if you put it on a two-dimensional torus, so the number match up. But more importantly, of course, we show that there's some smooth deformation you can do from the left-hand side, which is an X cube with decoupled two-dimensional toric code, and do some smooth deformation and map it exactly to the right-hand side where you have an X cube model on a slightly bigger lattice. Okay. And that explains a lot of things. For example, remember that the ground state degeneracy goes as 4 to the power of n, where n is the height of the system in the z direction. And that makes sense now because we know that we can grow the system by just keep adding these two-dimensional toric code. Or another way of saying it is that we can look at the diagram from the right-hand side to the left-hand side, and we can keep decoupling 2D toric code layers. In this way, we can decouple 1 layer, 2 layer, a bunch of layers, meaning that there are a bunch of hidden two-dimensional toric code layers in the X cube model. And because of all these hidden layers, not exactly give rise to the ground state degeneracy, which is 4 to the nth power. Okay. And secondly, now we know where the planons come from. The planons exactly come from these hidden two-dimensional layers. When you smush these two-dimensional toric code into the X cube, the planons all naturally just become the quasi-particle excitations of the toric code naturally becomes the planons of the X cube. And that's why the planons all have order 2. And that's why they have mutual statistics of -1. And that directly descend from what we know about toric code. And moreover, we know that the statistics between the planons would be short range, meaning that this planon would couple to maybe this one and this one, but it wouldn't couple to this one, right? Because they have to come from the same toric code in order for them to have statistics. If they come from very different layers, very different toric codes, then they wouldn't have statistics with each other, but this feature is exactly not true of what we see in the tridiagonal K-matrix, where the statistics decay exponentially and is non-zero, even though we're considering quasi-particles separated very far away from each other. And this feature, of course, is not only true, all these features, the first three features, is not only true for X cube, but also true for a whole range of models which share this feature, the foliation feature, which says that the three-dimensional fractal model contains a lot of hidden two-dimensional topological layers, right? And whenever this is true, we'll have a scaling of ground state degeneracy that's like integer to the power of height. And we'll have planons that come from the two-dimensional planes, and they will have finite order. They will have rational statistics, and the statistic wouldn't have very long range tails, which means that this 131 K-matrix as a fractal is definitely something different. Well, all we can say is that it's not foliated, that it doesn't have this feature of that you can decouple two-dimensional layers out of it and just to change the system size. Okay, how am I doing with time?
You're good. Take your time.
10 minutes maybe?
10 minutes easily, yes.
Okay, good. Right. So this is some of the first surprise that we got when we first started using this K-matrix to describe fractal order. But actually, this was not the original motivation that took us to consider K-matrix as description of fractal order, because originally we were trying to just use it to describe foliated fractal order. And indeed, there are K-matrix, this infinite dimensional Chern-Simons theory that does describe foliated fractal feature. That's, well, of course, different from X cube in an interesting way. For example, this is a K-matrix, which is so every layer has every row has three. Actually, I should say maybe in general 5 non-zero numbers. So 5 of the diagonals are populated, but otherwise it's 0 in periodic boundary condition. And we know that, for example, this one describes a foliated system, and it's very sharply different from the feature we see in the tridiagonal one, the 131 case. And we can immediately tell the difference by looking at the inverse of the K-matrix, because a lot of the key features about the K-matrix are encoded in the inverse, right? For example, the statistics is just explicitly given by the K-matrix. And when we take the inverse of the K-matrix and we compare it to what happens in the tridiagonal case, we see a very sharp difference. You see that in the foliated case, the inverse is still concentrated along the diagonal. Okay, only these diagonals are populated, and away from the diagonal is all 0. But on the other hand, if we have this tridiagonal, which we know is not foliated, what we see is that the inverse is non-zero everywhere. And if you look closely, you can see that if you do it for a bigger and bigger size of the matrix, you will see that the entry decay exponentially from the diagonal. The entry decay exponentially from the main diagonal, but still it's non-zero. And of course, that's exactly what we see from the statistics, because statistics is directly read from these K-inverse matrix. So we see that the statistics decay exponentially as the separation increase, but it's always non-zero, right? Not exactly 0. While for the foliated case, it should be exactly 0 beyond certain distance. And moreover, for the foliated one, for the case I showed you, we can explicitly show the foliation structure by manipulating the K-matrix, by doing some transformation on the K-matrix. And that was our original motivation to do this, to use K-matrix to study Fracton. Because in this case, when we're dealing with the K-matrix, we can see the foliation structure by simply applying some what we call W transformation. So it's a general linear transformation for the integer matrix, and we do it in the way of W transpose KW. And this is a well-known equivalence of the Chern-Simons term that you do this W transpose KW transformation. It describes the same Chern-Simons theory. And for our case, because now we have an infinite K matrix, we want to do it locally, corresponding to the picture of this one. We want to do it around the layer that we want to decouple. So we're doing a finite dimensional W matrix. So this looks pretty big, but it's only non-trivial within a finite block, okay? It's only non-trivial within the finite block. And when we do that, we effectively decouple these fields, and the dashed red block exactly correspond to the yellow plane that I draw here. So you can see they're decoupled because all the other fields do not talk to this set of fields. So in this way, we can use K matrix to figure out about this foliation structure in the foliated fractal model. And in this case, we find that what we decouple out is some Z2 cross Z2 twisted gauge theory for this particular example. Okay, and previously when we do this, we were dealing with exactly solo model, and as I said, the transformation we were looking at were local unitary transformation, so they're pretty complicated, and it quickly becomes too complicated to figure out. But for K matrix, I'm still hoping that we can have a simple way to see the foliation structure, although we're still working on that. Okay, so this is pretty much where we are regarding this infinite dimensional K matrix and Fractal. What we observe is that it can demonstrate some feature that's beyond exactly solo models, and it can capture the foliated feature. And for the foliated ones, we're hoping that this will help us to get more examples, not just the ones that we know from exactly solo models, which are quite limited. And also it would enable us to more easily calculate their property, for example, figure out how they're foliated, what kind of layers need to be inserted to get the foliation, to increase the system size. And moreover, we hope that this would enable us to study the equivalence of foliation structure using the K matrix formulation, that will be able to do local transformation to the K matrix and maybe insert extra layers and then see how the foliated ones are related to each other. On the other side, of course, the surprising discovery is that it can also describe non-foliated models. And for this part, we're much more basic in terms of our understanding. We're basically at the stage of identifying examples and get surprised by what we see and calculate their properties, understand what a fusion group is, understand what a statistics is. And most importantly, I want to understand if there's some similar way we can interpret their structure. That because for the foliated one, we have this foliation structure, which is very helpful in terms of understanding why the ground state degeneracy behaves like this, why the statistics behave like this. But for the non-foliated one, we now just have some data. And my hope is that we'll be able to understand, for example, if we compare the non-foliated model on different system size, how do they differ? How do we map one into the other in a consistent way that's kind of like an RG mapping, renormalization group transformation on the model. Okay, so I think I'm getting close to my time, although I do have a next part of my talk. I'll quickly give you the gist of it, which is to say that before we plan to go further, we spend a lot of time trying to convince ourselves that we're doing something legitimate, meaning that when we look at these 3+1D Chern-Simons theories, we are legitimately talking about local 3D model. And I was bothered by this because I was more comfortable with lattice model, and when we deal with a field theory, I'm not completely sure that these gauge fields are legitimate local 3D models. And that is important because we're trying to talk about 3D feature using these K-matrix, so we need to understand for what kind of Chern-Simons theory written in this way, that this is a legitimate question, that we're actually looking at real 3D physics. And so that becomes a major part of the work we did. And basically what we managed to do is to show that, so originally, of course, 20, 30 years ago, people were looking at, let's say, the tri-diagonal K-matrix. And there was no problem in that case, because you can write down a Laughlin wave function, you can come up with some Hamiltonian for it, and that's all fine. But here, we want to be more general. We don't want to just look at one particular K-matrix. We want to look at the whole class, and we want to understand what's the boundary of the class, that we can be safe. And it turns out that what we were able to show is that at least for what we call quasi-diagonal K-matrix, meaning that the entries of the K-matrix will be non-zero only along a ribbon around the diagonal. But beyond certain distance away from the diagonal, everything will be exactly zero. So that's what we call quasi-diagonal K-matrix. And of course, for integer matrix, you cannot get the entries to decay. So if they're zero, then they're exactly zero. So these are the quasi-diagonal K-matrix with entries populated near the diagonal. And for these set of matrix, we can show that indeed there's a legitimate lattice realization with local degrees of freedom. And we can calculate the spectrum using just the usual field theory calculation to see if it's gapped or gapless. And moreover, we can get a sense of the string operator that generates the plane now, that moving the plane. And that's also important because originally in 2+1D Chern-Simons theory, the string operator is, there's not much ambiguity about that. But once we try to extend the system in the third direction, there's no guarantee that the string operator will not extend with it, right? It's totally possible that even though it looks like a string operator, but actually it has extension in the z direction, so it's actually a membrane operator. And the excitation it generates is a string excitation, it's a loop excitation, not really a point excitation. So that's something we need to figure out. And that also become clear once we look at the lattice realization. So instead of walking you through the details of how the lattice model is written, let me just get to the conclusion part. So the basic idea is that we start from some stack of integer quantum Hall and let them couple to some planar U1 charge gauge field, and then integrate out the fermion, and then the gauge field would behave as we expected according to this big K-matrix. But let me just skip all this and tell you the some of the conclusions. For example, given a K-matrix, either 131, 141, or some other 101, 111, we can calculate the spectrum. Of course, this is known. This is just something we learned. And we can see whether it's gapped or gapless. For example, 131 and 141, 151, these are gapped. 101, 111, 121, these are gapless. And then on top of that, we can figure out about the locality of the string operator. And for the gap models, we find that the string operators are indeed local, although some of them might have exponentially decaying tail, which give rise to this exponentially decaying statistics, but they're still local in the sense that the tail is exponentially decaying. Okay, so this exponentially decaying tail is not just because of non-zero correlation length. It is something intrinsic to the topological feature of the system, which I still don't think I have a very good understanding, but that's all I can say, that it has to be there. It cannot be made zero, even though you try to turn the correlation length smaller and smaller, because it has to account for the exponentially decaying statistics between quasi-particles located at different height of the system. And on the other side, if we have a gapless model, then the string operator actually can become extensive and become a membrane operator. So there are lots of open questions from here. I will basically just set up the stage for further exploration. For example, we're currently trying to work out when is a K-matrix foliated and non-foliated from hopefully from a mathematical perspective. And one of the students I work with has a math background, so he's much better at working out the math than I am. So we're trying to take a K-matrix and see if it's gapped, and then from there figure out if it's foliated or non-foliated. And for the foliated one, the goal is that we can try to find equivalence class among them according to this local transformation that we can do. And for the non-foliated one, we'll just try to understand their general property, the degeneracy, the fusion group, and the renormalization group transformation of the model. And finally, the gapless one, we're still trying to get a handle on it. What kind of gapless model is that? Is that really stable gapless, or is it, if it's unstable, then what does it gap into? If it's stable, what kind of stable 3D feature is that representing? Is that some kind of spin liquid, or is that a gapless fractal model? We still don't know yet. So, yeah. And what about a non-quasi-diagonal one? So that so actually the axial model cannot be represented in this way, and that may have to do with the fact that it contains fracton, not just the planons. But that would be the next step. Would be to say, okay, we're not just content with having planons in our model, and want to actually recapture the fractal nature, and then and we might need to go into non-quasi-diagonal K-matrices, but yeah, that's further down the way. So yeah, that's all I want to say, and thank you.
Thank you, Xie. A wonderful talk. That means it's open for questions. I don't know if people want to type them or raise hands or unmute. I see Anton, you were first. Please go ahead.
Mm-hmm.
Right. Thanks for the very interesting talk. I would like to ask a little bit more about what you alluded to in the last part, namely the possibility of constructing the local models. Yeah. Because I'm a simple-minded person, to me it somehow feels important. So I understand that for a purely diagonal K-matrix, typically you can, at least in simpler cases, you have an idea how to construct a local model. Are there any other classes for which you would know how to do so? Of any other?
Right. Yeah. Let me just try to. Yeah. Thank you. Let me just try to delve a little bit deeper into the construction. So, like you said, if it's purely diagonal, then we know what's going on. If it's off diagonal, sorry, if it's not purely diagonal, but if the K-matrix is all, let's say, positive, like in the case of the tridiagonal 131 case. Then you can write down a Laughlin wave function, zi minus zj to some power. And so for that one, it's not a, you can come up with some Hamiltonian. It's not, of course, not exactly solvable, but of course we're pretty sure that first of all, the model is local and it's ground state of some Hamiltonian, and we can get a handle of that. So the cases we're trying to deal with this more general construction is, for example, if you have K-matrix with negative entries, and then the Laughlin wave function doesn't really work. So we're trying to capture, and that does happen. For example, you take even if you start from a all positive K-matrix, you can do some transformation, and then some entries might become negative, and that totally happens. So we need to be able to understand that as well. So what we did is that, like I'm showing here, that we take a bunch of integer quantum Hall layers. So every layer is described by a separate integer quantum Hall. So just AL, D, AL, and the coefficient is 1. So this is the little a describing the fermion state of integer quantum Hall. And then what we do is to say, okay, these fermions, they carry charge under different electromagnetic field. So we have multiple electromagnetic field. Of course, it's a toy model, but you can imagine that you have A1 and A2 and A3. And let's say the first 3 layers carry charge under A1, and 3, 4, 5 carry charge under A2, and 4, 5, 6 carry charge under A3. Okay, and this is represented, of course, by this term where we couple the charge in the interior quantum Hall layers to the corresponding gauge field according to how much charge they carry. So these are all in terms of these Chern-Simons terms. This is all standard. And then, of course, the idea is that we integrate out. We integrate out the fermions, and so there's some standard procedure you can do with the Lagrangian, integrate out the little a, and find out that the big A actually gives you, in this particular construction, it gives you the 131. And you can see where the 131 comes from, because this big A1, each big A couples 3 integer quantum Hall layers. So the self Chern-Simons term has a coefficient of 3. And mutually, the neighboring ones share 1 layer. So there's a mutual A1D, A2 term, for example. And that's where it comes from. So very naturally, all these quasi-diagonal K-matrix has a local construction like this.
Thanks.
Thank you for asking that.
Any further questions? There were a few during the talk. Maybe when people still think of questions, I wanted to ask a much more basic question. Actually, in the beginning, you started by asking about the relation or tying together the Xcode model and the gauge fields and the conserved dipole moment. And at that moment, I wondered, do you have any insights now whether or not, if I have a conserved dipole moment, I can call my excitations and conserved charge, of course, fractons, or are they still different objects?
Oh yeah. So this terminology is, of course, a physics terminology. So it's I think the consensus among the community is that if we see a point excitation whose motion, if we see a point excitation that don't move on itself, then we call it a fracton. And this can be in the case of XQ model, it can be originally a gap model, like the XQ model. It can also be like in the tensor gauge theory, where you have a gapless model, but with these gapped charge excitations. So they're all called fractal. And then if you have point excitations that move along a line or move in a plane, they are called the linear or planar excitations. This is just how we choose to call things. But of course, the underlying reason of why these things don't move can be very different. For example, there's one famous fractal model that I didn't even mention. This is the hard code that people were trying to think about. A three-dimensional model that without string operator, meaning that you can't just create a pair of things. And Zhou and Ha came up with this model where the process that it takes to create point excitation is a fractal. And that, so you create a set of 4 excitations at a time, and they're located at the corner of a tetrahedron. Just imagine a process where you pop up 4, but they're not at the corner of a rectangle, but at the corner of a tetrahedron. And then when you try to stack the tetrahedron, you take 4 of them, stack, and then you take the bigger structure, 4 copies, and then stack. And that leads to a fractal structure, and that's somehow how the point excitations can be moved. And that, I don't know how to interpret that as some kind of a dipole conservation. Of course, the hope is that we will be able to have a general framework and put everything under the same roof. But so in that case, of course, the excitation cannot move by itself because every time you pop out 4. And it seems to not fall into any of these foliation structure or any of these picture that we're trying to come up with. So I guess I'm just trying to say that even though we see fracton feature in this diverse range of models, they can be due to very different physical mechanism, and we don't have a general understanding of everything.
Okay. Perfect, thank you. Any last question, perhaps? Doesn't seem to be the case. So thank you very much again, Xia, for contributing to our long-range colloquium.
Yeah, thank you for having me.
And thanks to all of the participants for joining and for participating.
Thank you.
Thank you.
All right. Have a wonderful day, everyone.